Can you see the screen?
باين.
مبين عندكم lecture 2?
Yes.
Okay, good. So we can start. I guess it's 12 o'clock. So lecture 2, today we will continue with the semiconductor fundamental, where we will describe the energy band model, the band gap between the two states or two band energy of semiconductor. Then we will describe, or we will give you the result of the density of a state of electrons inside semiconductor. And before that, what I will do is I will go through the derivation of the density of a state of electrons of a free electrons and compare it or just make implement to the electrons inside the semiconductor. And of course, we'll introduce the doping material to the pure semiconductor material. Okay, so now if we are looking at the silicon atom, since the silicon atom is the elemental semiconductor material, pure material, here we're talking, we know that the band structure of this silicon is either valence or conduction band. So let's see how we can present them in this slide, okay? So in this slide, the energy band diagram, as you're used to it from last year, so we'll say we'll present it as a flat band. We'll say we have a conduction band and a valence band. Between the conduction and the valence, we have an energy gap. So the energy gap energy is EC minus EV. So these flat band that you see here represent the lowest energy, like EC is the lowest energy level in the conduction band. EV is the highest level of energy in the valence band. And we know as silicon that pure silicon, all the electrons are sitting in the valence band and the conduction band is empty. As I said last lecture, that what you will have is in order for electrons to move from the valence band to the conduction band, you do it either by temperature changing on the material, which will cause it to jump to the conduction band, so it have to have enough energy to pass the energy gap band. And the energy gap is given, you know, like it's specific for every material. It's not the same. So every material has a specific energy gap. So we say then that the electron energy will be increasing in this direction. That implies that the holes, which we call them holes, the vacancy that will be in the valence band, it will be increasing downward. Okay, and we're taking the distance in this direction. Okay, so simplified version, we said that from the previous slide is that we present the energy band diagram as a valence and as a top band conduction band. And we said that the energy gap or band gap energy is assigned to as EG, which is the separation between EC and EV. So again, saying, what do we mean by that? We said that the electron increases its energy this way. So if we have an electron sitting in the valence band, so it increases its energy when it starts moving, as you see, to the conduction band, leaving behind, if we are talking about a pure material here, so for every electron that goes up to the conduction band, it has an empty, or what we call it, a hole left behind in the valence band. So the conduction electron, so we call these now as a conduction electron. We say this conduction electron occupies a state in the conduction band. So now we are in a band, but really we don't know how much energy it has. So we don't know at what level of band state it's sitting, because we know that the conduction band has so many states in it, and this electron is sitting, occupying a specific state in the conduction band depending on its energy. And the hole is occupying the same thing. We say we treat the hole as positive charges, and we say that this hole then is sitting in the valence band at some state. So it's an empty state in the valence band. So electrons and holes tend to seek lowest energy positions. As you see, we said that the electrons tends to rise up, so, and the holes tends to float down. So it's like you are saying, what you are saying, that if you look at bubbles of water, that will represent the holes. So electron kinetic energy is upward, so it's increasing. And for holes, the increase will be from up to down. So this is the direction of kinetic energy for holes, and this is the kinetic energy for electrons. And again, we said that the energy EC represents the electron potential energy. And of course, this is the lowest energy level in the conduction band. So you always, if you want to measure the potential energy of the electron, you will say it is from the EC to some energy level. So we call it E reference. So it's different from the free electron. The free electron has a constant energy, okay, while in the semiconductor, the electrons are moving. So we say this is depend on which state it has set, and you're measuring it from EC. So your EC is like your zero level and going upward. Okay, so now we say, okay, what's the potential energy? Potential energy of a charge then is equal to minus QV. What do we mean by that? We're saying that the potential energy of a charge is related to the potential or to the electrostatic potential V of X, depending on the direction of the charge. Yes.
Can I ask a question?
Sure.
What is the meaning of E reference, energy reference, in the previous slide?
Previous one, so we'll go and we'll say, okay, this is the previous one. What we are saying, okay, as you will see later on, when we want to calculate the concentration of electron, إذا أنا بدي أعرف قد إيه عندي إلكترونات موجودين بالconduction band بهيدا الريجن. I have to know first how many states are occupied، يعني قد ايه عندي states of energy وين موجودين هالإلكترون، لا أقدر أعدهم. أنا ما بقدر أعرف على كل state إلا لحتى أعد الإلكترونات. ف my reference level will be EC، يعني بقلب كل material EC will be known, the conduction band energy will be known, the valence band will be given. يعني إذا قلت لكم اليوم هيدي السيليكون ماتيريال، بقول لكم السيليكون ماتيريال عندها energy gap equal to that، EC equal to that، EV equal to that. فصار ال EC إذا أنا بدي أشوف بأي E موجود الإلكترونات لحتى أقدر أطلع الكونسنتريشن، أوكي، معناتها بدي أقول E minus EC، يعني كأنه my zero level هي EC، مش ضروري تكون زيرو، يعني أنا عم بقيسها من ال EC قديش موجودين بالكوندكشن باند. إذا بدي أحسب الهولز اللي هن بعتبرهم positive charges، بقول قديش عندي أنا مثلا energy أو قد ايه عندي concentration of holes بقلب الفالنس باند، بقول مثلا نقول على هالليفل على E1. E1 بالنسبة للفالنس شو عم بتكون؟ عم بتكون EV minus E، لأن ال E1 هي below EV. هون ال E مثلا EX لنقول EX هي above EC، فبقول EX minus EC. وضحت؟ اوكي جريت.
يعني ال E reference ممكن تكون EC or EV.
ايه
ناخدها بالنسبة
بقلب كل باند. اذا انا عم بحكي بالكوندكشن باند بقول EC، عرفتي كيف؟ ماي ريفرنس. اذا كنت عم بحكي بالفالنس باند بقول ماي ريفرنس هي EV. حتشوفوا بس نعمل derivation لكل concentration كيف نقدر نعملها وكيف بنروح كريفرنس. يس.
بس قبل ما ترجعي هون ما فهمت لما حكيت عن الدايركشن للانكريزنج هول وانكريزنج الكترون انرجي كيف؟
اوكي انا مش عم بطلع من هون عندي الكترون هون، مش اعطيتها temperature so it's temperature dependent لنقول، مش بعدنا عم بحكي بيور. لو كانت دوبينج بده يكون عندي هالماتيريال الثانيه اللي دخلت واعطيتها لنقول it's a donor electron، بتكون قاعدة هون، الدونر بيبقوا قاعدين هون، لأنه ليه؟ لأنه بيكونوا أقرب للكوندكشن باند، بقوم بيعمل الجمب لهون، معناتها الانكريزنج الكترون انرجي عم بيطلع، قلنا هيدا الليفل اوف انرجي أقل من هيدا، فمعناتها الالكترون having an increased energy in this direction. بينما كبوزيتيف تشارجز عندهم the top level هو EV، معناتها لما تركت الالكترون تركت vacancy down here، او كان عندي acceptor لنقول قاعد الكترونات هون نزل نزول، فعم نقول the increase of energy going down لقلب الفالنس باند. Clear to everyone? I guess so. So let's continue then. We talked about potential equal to QV, where V is as a function of distance. We're saying electrostatic potential V of X, so we relate the potential, energy potential, to the charge times voltage, where V is equal to 1 over Q, E reference minus EC. So here again, what I'm saying that the E reference is where the electrons are found in the conduction band, so it's E minus EC. Usually we write that, we will say that the electric field equal to minus dV by dx, so it's equal to 1 over Q dEC by dx. Okay, so you're integrating with respect to the energy of the conduction band. And since we're talking about electron.
اي ريفرنس بتصير صفر derivative لها.
نعم electric field هو derivative للpotential as a function of distance, and because we're talking about electrons have negative sign هون. لو كنا عم نحكي عن الهولز حتلاقوا انه positive. اوكي هي تشارج نيجاتيف حيطلع الالكتريك فيلد للالكترونات بالنهايه they both will have the same unit، يعني ما بيكون في عندهم negative charges لما بنعمل لهم comparison. اوكي طبعا هو الديريفاتيف. اوكي هون عم بس بفرجيكم انه how it's really moving as a charge. Okay, variation of EC with position is called band bending. So هيدي الكلمة حتشوفوها وحنعيدها وحنشرحها شو معناتها. وهون عم بيقول لك الباند بندنج هي بتساوي ل 0.7 الكترون فولت. اوكي حتشوفوا من وين اجت هيدي ال 0.7 الكترون فولت. لانه ليه؟ لانه عم بقول اذا عندي فولتج هي 0.7 فولت كأنه عم باخذ the built-in potential. اذا بتتذكروا بالسيليكون حكينا عن البيلت ان potential اللي هي 0.7 فولت. اوكي before any external potential، يعني نحن هون عم نحكي بس due to the movement of electrons بقلب السيميكوندكتور without any doping، يعني عم نحكي كماتيريال without any external electric field. عم نقول كbuilt in potential due للmovement of electrons from the valence band to the conduction band due only to temperature raising، فاعطاني potential drop of 0.7 volt. فهيدي اذا عملنا لها طبعا as a function of position حيعطيني 0.7 electron volt. Okay, when we are measuring the energy gap, which is EC minus EV, the energy difference between the conduction band and the valence band for material, we're talking about the minimum energy of photons that being absorbed by the semiconductor. So that's what we are trying to say. As I told you, every material have a fixed energy band gap energy. So EG for gallium arsenide is 0.67, for silicon is 1.12, and for gallium arsenide, so that's a compound semiconductor, is 1.42. Gallium arsenide is very important in optical devices used to, in laser optics to measure the light and the wave propagation. Okay, so now we are going to start with the density of a state. On this slide, you will see in a second the solution or the density of a state of electrons in the conduction band and in the valence band, so it's inside the material. Now, the following slide, I will show you how did we reach to that equation, since what I'm saying is that N of E dE, okay, N of E is the density of a state. So N of E dE is the number of states per cubic centimeter in the energy range between E and E plus dE. So what I'm saying, I'm going through energy. Let's say this has an energy E, and this energy here, it's E plus dE. So I want to take the number of a state here, number of a state, per cubic centimeter, okay, so in a unit volume, meaning, and see the energy that it's really taken between this energy and that energy in order to obtain the density of a state. Why do we need to obtain density of a state? As I said, if I know the density of the states that electrons are occupying, then I can integrate over that region to obtain the concentration of electron. Now you're telling me, why do we need concentration? We need the concentration of electrons as well to calculate the concentration of holes so we can obtain the current. Current depends on the concentration as well as it depends on other parameters in the semiconductor. So we'll do step by step. Okay, so near the band edges then, we'll see N of C, which is equal to 8 pi square root of 2 over H cubed, ME effective dust to the 3/2 the square root of E minus EC for the energy E أكبر أو بتساوي ل EC. So I'm talking in that region now. In the conduction band, the density of a state here is given, and as you notice, it depends on the mass of the electron. Now the sign, the effective mass, because it's inside the material, and in a minute I will show you what do we mean by effective mass and how can we calculate the effective mass. Again, for every material, the effective mass of the material of the electron will be given relative to the free mass, to M0. The same thing we can get for the density of a state of holes, okay, which is 8 pi square root of 2 H cubed MH effective dust to the 3/2 the square root of EV minus E, since EV is here and going this direction where E is below EV, so E is less than EV. Now these are the results, and sure, I will show you how we obtain these two equations from free electron, since to deal with electrons inside the semiconductor is very complicated. So what we do, we treat the electrons as a free electron in space, and then we will say that since the energy depends on the momentum, we look at the effective momentum, and the effective momentum will say, can be summarized that the only change with it will be due to the masses of the electrons and holes. Okay, before we move to the derivation or to the explanation how we obtain these two equations, first I will tell you that, okay, the effective mass of electrons with relative to the free mass M0, which is a constant. Okay, it's for silicon, it's given to be 1.08. For germanium, it's 0.56. For gallium arsenide is 0.067. So what I mean by giving you this table is to tell you that for every material, when we try, let's say, to do some application, for sure, if I ask, let's say, to determine the density of a state of electrons, I should be giving you a table which contains the relationship between the effective mass and the free mass, and as well inside the table you will be given all the constant that we in the first lecture I have mentioned. Okay, so now I taken this instead of my handwriting, I took it from your textbook, okay, where I'm showing you here that 2 pi over L. What do we mean by 2 pi over L? 2 pi over L is the space between the K vector. So now we are talking about semiconductor. We're saying that a semiconductor has a cube structure, or let's say we want to calculate the free electron. So we'll consider a cube structure, and we'll say the cube structure have a length of L, and then between each electronic state, you recall when we did, and we said that the energy is between this state and this state, and the difference is dE. So here we're saying between this K vector and this K vector, it's 2 pi over L. Why? Because we know that every electronic state then in the K space will occupy then, since it's a cube, 2 pi over L cube. So each electronic state then equal to 8 pi cubed over V. Now, if I want to know the number of electronic state, I have to know the volume of the total electronic state. So let's assign, and we'll say that this solid angle, we call it, is the volume of the whole space, of the K space. Then we will say that the number of electronic state, I can then calculate that the total volume over each electronic state volume will give me the number of electronic state. So the total volume of the electronic states over one electronic state will give me then the total number. Now, why do we need the number of electronic state? You will see in a minute why. The reason for that is that, okay, now I want, let's say, to calculate the density. I will take two spheres. I will take a K and a K plus dK radii sphere in order to obtain the area. Okay, the area between these two spheres is 2 pi K dK, but instead of area, we will go through volume, because what we want is the density, and the density is, we said it's per unit centimeter cube. So we are talking about volume rather than area. So I will take a sphere of radii K and another sphere of radii K plus dK, and then take the difference between them to obtain in this shallow here the volume of the two spheres. Okay, so let's do the calculation then. Okay, the energy then is given by what? P square over 2m0. So we are talking about energy that is given in terms, okay, in here it's written h bar square K square over 2m0, where h bar is really equal to h over 2 pi. So we eliminated the pi from the energy equation. So we are talking then, and this came from, of course, the solution to Schrödinger equation, treating the free electron problem. And in that, what we want to do then is to derive, saying that in the number of electronic state, then we want to find first the volume between K and K plus dK. Okay, so the volume will be equal to 4 pi K square dK. You can obtain that, you know, by doing the writing down both in order to obtain the 4 pi K square dK. Okay, knowing that for each state you have 2 pi over L cube. So going now, we'll say, okay, from these two, from the solid angle over the each state volume, gave me then k square dk over 2 pi square v. Why do I need this then to go back and replace in order to find the energy? Why? Because the density of a state, okay, we say that the density of a state, okay, going from one energy E to E plus dE per unit volume is defined as N of E dE. And I need to obtain N of E, the density of a state, then I will take this and divide or take the derivative of it with respect to energy. Okay, so let's start then from this equation here. I write N of E dE, okay, which is equal to k squared dk over 2 pi square. Okay, which is that, since it is the number of electronic state in a unit volume, okay, so per unit volume, so the v cancel out and you will left with k squared dk over 2 pi square. Now we can substitute, instead of k and dk, we will put it in terms of energy. So we will obtain k squared dk equals square root 2 m0 to the 3/2 e to the half dE over h bar cube. Recall from the other equation that you have, we obtained that we got the 8 pi, and then we have to take into consideration from h cube to h bar cube, so the 8 pi will get out. Again, from m0 that you have here to the 3/2, we substitute instead of it me effective, okay, to the 3/2, and e to the half if we are talking about electrons, so it's in the conduction band, so it's the n of the conduction band, so it will be E minus EC to the half dE. So again, if we go to the equation, the last equation here that you see, it's N of E equal, I put here 2, I added 2, so it's root 2 over 2 m0 to the 3/2 e to the half pi square h bar cube. So this is the density of a state of electrons, of a free electrons. From this derivation, we can take this equation and go back to the previous one. Okay, in here, so look at this equation, it's exactly the same. Instead of ME, I had it M0 for free electron to the 3/2. Instead of E to the half in the free electron, here it's E minus EC to the half. And instead of H bar pi square H bar cube, here we have 8 pi over h cube. Okay, the root 2 over 2, I added here 2. The reason for this is because we have to take into consideration the spin orbit of the electron. So we have electron is half a spin, so for 2 we have to take into accounting for the half. So this 2 here then, if you don't find it in your textbook, if you read in, I recommend that to understand this course, you have to read a lot. We can't cover everything in class. I try, and what I can do is even I can go over this this derivation, I can do it, you know, like in detail, make an image for you and send them in a file as a PDF on the group. So like that, you all have access to the PDF file. So every derivation that is not included in the PowerPoint slide, I'll try to do it unless I ask you to do some yourself. Then it will be an exercise or a challenge to you to go. Let's say, for example,
الديريفيشن مطلوبة.
هو الديريفيشن اللي مطلوب بهذا الكورس. derivation والintegration. اوكي؟ يعني أنا قلت من قبل إنه هيدا الكورس هو physics مش devices. يعني بدنا نفهم كيف عم بيتحركوا الإلكترونات، بدنا نعتبر الهولز عم بيتحركوا، شو العلاقة بينهم وبين الماتيريال، كيف هالماتيريال مع الموشن تاعت الإلكترون عم بيخلق عندي كرنت، الكرنت كيف عم بيعتمد عليهم، حتى بس نوصل للبي ان دايود وللبايبولر. قولي ما حنعمل له كفر، حنعمل للفيلد افكت وللميتال مع السيمي كوندكتور. فكلياتهم الهدف منه هو هيدا الكترونيك ديفايسز. هالالكترونيك ديفايسز كيف وصلنا لهالكرنت انه اللي عم بيمشي فيه؟ بدنا نعرف يعني لما بيكون without an external كيف طلع معنا 0.7 for example of the PN diode، وكيف لما حطينا an external field شو طلع معنا ككرنت. يعني بدنا نحسب الكرنت. هيدي الكونستنت اللي كنتوا انتم مثلا بسنه ثانيه تقولوا انه the diode current equal to some constant I0 e to the EV over KBT، اوكي، minus 1 between bracket. يعني نحن هون كنا عم نعتبر انه عم ناخذ هالايكويشن without knowing how did we arrive to that equation. هلا بهيدا الكورس نحن بدنا نروح ان ديتيل ونشوف كيف الريليشن شيب بين كل بارامتر والتاني. اوكي، طبعا نحن هون بكل السيمي كوندكتور they apply Schrödinger equation، ونحن بنعتمد بس على السوليوشن. يعني وقتنا مش انه لحتى نروح كيف وصلنا ل time dependent or the solution of a Schrödinger equation for time dependent. and كل الهدف انه نعرف بس انه عندنا kinetic energy اللي هي P square over 2m effective، لانه هون عم نقول بقلب السيمي كوندكتور بطلت P square over 2m زيرو، ولهالسبب شايفين هالساين شو عم بتقلكم roughly P square over 2m0، لأننا ما عم نعتبر الانترنال forces. يعني ما عم نروح 1 by 1 بقلب شو عم بيصير، عم نقول خلينا نعتبر إنه المومنتوم بس عم بيعتمد على الإفكتيف ماس. يعني شو عم الالكترون تغير الماس اللي إلها بقلب السيمي كوندكتور، باقي ما تبقى باقي الفورسز ذا سيم كل شيء، فبنعتبر انه هي المومنتوم بقيت ذا سيم، دي كي فاكتور بقي ذا سيم، بس اللي تغيرت هي الماس، ومن هون بنطلع الانرجي. اوكي، إذا قلنا السيليكون مثل ما شفتوا قبل إنه هالإنرجي جاب عنده إنرجي جاب هي 1.12 إلكترون فولت، عنده الفالنس باند هي completely filled، عنده الكوندكشن باند هي completely empty. أوكي، وإتس a semiconductor. قلنا إنه لو إنسوليتر بيكون الإي جي كتير كبير، ما في مجال انه لالكترون حتى لو we raised up the temperature انه تطلع الكترون من الفالنس باند على الكوندكشن باند. واذا كنا عم نستعمل ميتال، وحتشوفوا بالميتال طبعا ما عنده، لانه الاي سي والاي في they overlap، يعني عندكم الكترونات موجودين بقلبهم، فما في energy gap، بنقول no band gap. فإذا السيليكون هي الانترميديت بين الانسوليتر والميتال، ونحن هيدا انه we can use it as a very good electronic devices. Okay, so in here what I'm saying, if it's silicon dioxide, what do we mean by silicon dioxide? We mean it's an insulator. As you will see, when we want to separate between a region and a region, we'll put an insulator, so not to allow any electrons to move from one region to the other, or any electric charge to move from one side to the other. So silicon dioxide has a very large energy gap, so it's referred to it as an insulator. Now on this side you will see the metal, a metal which have the EC and the EV, they overlap, so it's all filled. There is no energy gap between them. Now we'll just, it's a generalizing. Instead of just having, we say a silicon, a pure silicon material, and the concentration or the chance of having an electron in the conduction band will be due to a raised temperature. Now we'll say, okay, if I add another atom to the silicon atom, from column, here I'm saying from column 5 and from column 3 element, meaning that if I add from column 5 meaning what? Meaning that it has 5 electrons in its outermost shell, so this column will be donating an electron to silicon, so we will say this is an N type, meaning giving extra electron to the silicon, while the table 3 element has 3 electrons in its outermost shell, so it's gonna take an electron from silicon and having it leaving a vacancy in the silicon atom. So we will say this is an acceptor. This column is a donor atom. So donor meaning it donate, it gives electron to silicon. This is an acceptor, it takes an electron from silicon. Okay, so here we're saying that from table 5 then, from column 5 in the chemical table, we have phosphorus, we have arsenide, we have other material. So we're showing that it has 5 electrons in its outermost shell. So there is an extra electron that will be unbounded from the donor, leaving behind to join and bound to the silicon atom. So the density then here is referred to an ionized donor density. Okay, so the density of the donors are called ionized donor concentration. And we'll say, you will see why we call it ionized, because it's ions. We're looking at it as a charge. Acceptor, we said the acceptor comes from the column 3 in the chemical table, which is a boron atom, which aluminum, gallium, odium. Okay, so in all these from table 3 or from column 3, meaning that it has a missing or not missing, it has a vacancy that can take an electron to share with the silicon atom, with the lattice, so it's taking away from it and leaving a hole to the lattice atom, or to the mother atom, we call it. And in this case, we will call it ionized acceptor concentration, because it left a positive ion into the semiconductor material. Okay, so here, this slide, you have seen it in third year, when in second year, where I presented to you the silicon atom as we have an acceptor, okay? Okay, so the arsenide, we said the arsenide is the loosely bound fifth valence electron of the arsenide atom, breaks free and becomes a mobile electron for current conduction. So it has 5. So one of the electron will be loose and will be used for current conduction, meaning it will be sitting underneath the conduction band. Okay, so this is the donor where all the electron charges are sitting. So that's why we call them ionized donor. Okay, so the energy sitting in here, all what it will be doing is ionized, we said donor ionized energy. And now if we are talking about boron atom, which is an acceptor, so it has taken all the electrons from the valence band and sit in here. So that region then is called the acceptor ionized energy. Okay, here I just given ionized energy as EC minus ED or EA minus EV as well. You're not going to go through the derivation of the ionized energy. If you are talking about donor energy or acceptor energy, will be given with respect to the conduction energy or with respect to the valence energy for the material. So you will see all the all the values of ionized energy given to you in terms of milli electron volt. The purpose from here is just to understand that if I have a donor, that means it will give electrons from its atom and it will have energy sitting in here, which then can be calculated with relative to EC. Okay, the same thing for the acceptor. It will be taking electrons from the valence band. So we are measuring this energy level between the valence band and the energy state of the acceptor in order to find the ionized energy. Okay, if we look here, we say, okay, at 0 degrees Kelvin, the electrons that were donated from the element in the column 5 will be sitting, all the electrons will be sitting here. If I increase the temperature, then some of the electrons from the ionized level will go into the conduction band until I reach to room temperature. Then at room temperature, all my ionized electrons will be in the conduction band. And if I'm talking about the acceptor atom, which has taken all the electrons from the valence band, so they will be sitting here as we increase the energy, and they will be all at room temperature sitting and leaving all these vacancy in the valence band. Okay, charge carrier concentration. We will say here charge neutrality condition. Okay, because for intrinsic material, we know that P equal to N because ND is 0 and A is 0. if we are talking about a pure silicon without doping, without having a donor or acceptor. But the charge neutrality equation, then you have to recall and you have to remember that the donor plus the hole will always equal to Na plus N. So if I'm talking about a material that have a donor in it and an acceptor, we said that the donor density plus the holes that are in the valence band at room temperature is equal to the density of acceptor plus the electrons in the conduction band. This equation at thermal equilibrium will always be true if N equal to P, or if N does not equal to P, NP, the product of the electron concentration with hole concentration, equal to Ni square. And this equation, we call it the law of mass action. Of course, all these will go over it once we do the concentration of electrons and the concentration of holes, when we integrate over the distribution function where the electrons can be found or the holes can be found. Here it's only we're doing some manipulation to these two equations, which since we introduce a donor atom and an acceptor atom, so the concentration of electrons becomes related to the all known material, if you want, the Ni square, depending on the material we use, and the doping and acceptor material. So N can be calculated and P can be calculated from these two equations. So you just substitute, for example, if I want N to obtain the concentration of N, so I can substitute for P here. I will put it's equal to Ni square over N, Ni square over N, and then I will say Nd plus Ndn plus Ni square equal to Nan plus N square. So we eliminated the from there. Then we will say N square plus N into Na minus Nd minus Ni square equal to 0. So we have the quadratic equation and we solve for the quadratic equation in both the same thing. If I want P instead of N, so I will say P equal to Ni square over N. So we said carrier concentration depends on net dopant concentration. Okay, now we as well seen with devices an N-type material and a P-type material. What do we mean by N-type material and what do we mean by P-type material? We said in N-type material, mainly it's the donor density or the doping. So we have a donor to get a donor density. So the donor density will be minus the Na will be much greater than Ni. So in that equation, why we put this? Because we said always Np, if we have N-type or P-type, Np equal to Ni square. If we're talking about P-type material, then P is greater than N, and in this case the density of acceptor is greater than the donor density, and in here we will have Na minus Nd much greater than Ni square. Now in here what we are presenting is that if we are talking about an intrinsic material, which we are comparing Ni to Nd, to the donor, density, we have this slope, while if we are talking about extrinsic material, you notice that it will be in this region. It's like a freeze out, okay, and the axes are as a function of temperature, and here it's the concentration with respect to ND. Okay, so this is from here, you will see that this curve that we obtained based on here, we started from 0, okay, and this 0, n equal to 0, so at k equal to 0, so that means there is no electrons in the conduction band. Once the conduction, as a low temperature, the concentration of electrons start to have the ionized donor density. Sorry, we haven't, okay, finished. Okay, have the, as we increase into moderate temperature, where we will be using the moderate or room temperature, you will find that N becomes the total donor density. So let's say, for example, if we have a numerical calculation and you're given the donor density, so you can easily, since we are talking about moderate temperature, at room temperature, we can always say that the electron concentration equal to the donor concentration, and you will use this this unit and continue with your calculation. Of course, as the temperature goes very high, you're going back into the dominant, into the Ni, because we said that the concentration of electrons in intrinsic material, it's due only to temperature. So in this case, N be the Ni, the intrinsic concentration. So now we reach to the some notation or terminology that I will go over what we have done. So we said the donor mean impurity atom that increases N or being doped into the material and found into the conduction band. Acceptor is the impurity atom that increases P. N-type material, meaning containing electrons more than holes, and P meaning containing hole more than electrons. And when we refer to something, you will find later on, we say majority carrier, minority carrier. So if I'm saying, let's say an N-type material, which will be the majority will be N, the minority will be P. If I'm talking about P material, I will be having the majority P and the minority N. If I'm saying an intrinsic material, then N equal to P equal to Ni. For extrinsic material, meaning the semiconductor, the pure semiconductor is being doped with either a donor or with an acceptor. And we said that the majority carrier concentration is the net doped concentration. In summary then, yes.
بس بليز كيف قلنا بالبي تايب كان عندنا هولز اكثر، مش هو بس الالكترون يطلع من الاي في للكوندكشن باند بصير في هولز، فكيف الهولز اكثر من الالكترون؟ يعني المفروض كل هول
لحظة ما شو قلت أنا؟ قلت لو كان شايفي هون هيدي الإيكويشن شو عم بقول؟ N equal to P equal to Ni. هون عم بحكي عن impure material. هون عم بقول إذا كان عندي a pure silicon and I found electrons in the conduction band, meaning due to temperature, then the amount of N will equal to the amount of holes that is sitting or left, electron left it, left this vacancy in the valence band. لما عم بحكي هون عن N-type material and P-type material, I said this N-type material due to what? To a donor atom. عمل increase للN. أنا عندي semiconductor. جيت بهالسيميكوندكتور شو عملت؟ عملت له دوبينج من one side of an N-type. يعني قمت جبت فوسفورس اللي عندها 5 إلكترون بالأوتر موست شيل وحطيتها بقلب هالسيليكون. شو عملت؟ قالت اوكي انا حاقعد هلا عندي انرجي حاقعد just below the conduction band until I will have enough energy to go into the conduction band and form the concentration N. في يكون بهيدي الالكترون بس N type، يعني ما زدت انا an acceptor، انا عندي بس N type a donor، وعم بقول فاذا صار عندي the number of electrons زاد عن ال number of electrons of silicon material لو كانت pure. اوكي، بهيدي الحاله صار عندي majority هن N والماينوريتي هن P. انت هلا عم نحكي ك1 الكترون بس يكون العدد ND the density donor the donor density يمكن بيكون مثلا 10 to the 16 of per cubic، يعني 10 to the 16 atoms per cubic centimeter. فانت عم تحكي هون عن N type اللي زادت كثير عن ال ND، عن الدنسيتي للهولز. إذا جينا قلنا أوكي طيب أنا عندي سيليكون ماتيريال وحطيت لها بي تايب، يعني شو عملت؟ جبت بورون أتوم وزدتها ضفتها على السيليكون، فقامت هي شافت إنه والله السيليكون عنده إلكترون زيادة، أنا حآخذ هالإلكترون منه وحطها عندي، آخذها أنا. فشو عملت لما أخذت إلكترون؟ من وين بدها تاخذ الإلكترون؟ من الفالنس باند. أخذتها من الفالنس باند فصار عندي ليفل اللي هو above the valence band قاعد فيه الإلكترونات اللي راحوا على الأذر أتوم، على اللي خلق لي vacancy بقلب الفالنس باند اللي بسميه بي تايب، يعني صارت السيليكون اوف ا بي تايب عندها اكسس اوف فيكنسي اكثر ما عندها الكترونات. اوكي، بعدنا عم نحكي كان تايب لوحدها وكبي تايب لوحدها. اذا عندي ان تايب ماتيريال بيكون الماجوريتي هن ان والماينوريتي هن بي، اذا كنت عم بحكي عن بي تايب بيكون الماجوريتي بي والماينوريتي ان. إذا كنت عم بحكي عن pure material the N equal to P، لأنه عندي كله vacancy بمطرح والإلكترونات بمطرح تاني. حتى لو ضفت أنا لنقول لو ضفت temperature، يعني عليت التمبريتشر على السيليكون اللي حيصير إنه قديش حينتقل الإلكترونات من الفالنس على الكوندكشن، حيترك ما قبيلهم amount اللي هن بسميهم P اللي هن بالفالنس باند. وضحت للكل؟
ايه دكتورة، thank you.
اوكي، فإذا in summary منقول the valence band is the highest nearly filled band والconduction band he is the lowest nearly empty band. اوكي، بالنسبة كسيليكون عم نحكي وعم نحكي كباند، نحن عم نقول الانرجي allowed electron energy level in an atom give rise to band of allowed electron energy level in a crystal. بيكون عندي هي الفالنس باند هي اعلى نقطة اللي مثلان عندي فيها الالكترونات، والكوندكشن باند هي اقل انرجي ليفل وين الباند هو empty. وقلنا الانرجي جاب بين الاثنين هو بنسميه EG the energy gap. واذا كنا عم نحكي عن سيليكون قلنا عنده 1.12 electron volt at 300 degrees Kelvin، عم نحكي at room temperature. Okay, again we said that the electric field is equal. There should be a minus sign here unless we're taking the absolute value, so not to confused between electron and holes, but it's minus dV by dx. Okay, and E minus EC represents the electron kinetic energy. So we are talking about kinetic energy between the energy where the electrons are found with respect to EC as my reference. If we doped, then we say that we have ionized at room temperature, and the group element for 5, we call them donor. The group 3, we call them acceptors. And the dope concentration, we said, typically is around 10 to the 15 per cubic centimeter to 10 to the 20 per cubic centimeter. Here, when I told you about if we're talking about acceptor or donor, depending, we're not talking about a single atom, we're talking about a typical values between 10 to the 15 to 10 to the 20 per cubic centimeter as a doping concentration. Thank you. So we'll go back. And I see that we can stop recording now. And if you have a question, sorry, we can continue. Okay.